In lesson 9.1, you used h equals negative 16 t squared plus c to find the height h above the ground of an object falling from initial height c at time t. Remember the baseball? If an object projected into the air given an initial upward velocity v continues with no additional force acting on it, the formula h equals negative 16t squared plus v times t plus c gives its approximate height above ground. Example problem 2, using the vertical motion model. During halftime of a basketball game, a slingshot launches t-shirts at the crowd. A t-shirt is launched with an initial upward velocity of 72 feet per second. The t-shirt is caught 35 feet above the court. How long will it take the t-shirt to reach its maximum height? What is its maximum height? What is the range of the function that models the height of the t-shirt over time? We will use the equation below to model the height of the object, and we're going to substitute in, recall, 72 feet per second, or the object's initial velocity, in place of v, which, if you recall, v was the coefficient of our linear term. So here we have the equation. H equals negative 16t squared plus 72t, note the 72 is the initial velocity of the t-shirt, plus 5. Take a moment to consider 5. 5, if we were considering a graphed parabola, 5 would be the y-intercept. In this case, 5 is the initial height off the ground of the t-shirt. Our equation gives the t-shirt's height, h, in feet after t seconds. Since the coefficient of t squared, note our leading coefficient negative 16, since that's negative, the parabola opens downward and the vertex is the maximum point. So let's continue and find the vertex much as we have in the past. First, we'll find the x-coordinate of the vertex, then we'll use that to find the y-coordinate of the vertex. Recall the x-coordinate of the vertex is negative b over 2 times a, and for us, considering the equation above, the negative of b is negative 72, 2 times a will be negative 32, and that reduces, and specifically reduces to 9 over 4. And that, recall, is our x-coordinate of our vertex. And then we can use that to find the y-coordinate as well, simply by substituting 9/4 in for t in both places and solving for h, which will represent what we customarily consider to be our y value. Having done some calculations, we find that our height at the vertex is 86 feet. So what that means is the shirt reaches its maximum height of 86 feet after 9/4 seconds, or 2.25, 2¼ seconds. So let's consider with a very quick sketch, not that quick, there we go, with a very quick sketch what this is representing for us. Recall the y-intercept of 5, the t-shirt's height at initial launch. We have a maximum here. Well, now you can probably begin to see why 2.25 is valuable for us. I think it's easier for us all to think of 2.25 than 9/4. But the maximum height is reached somewhere around here if we let this height be 86 feet and this height again 5 feet. And there is 2 seconds, and we'll say there's 3 seconds. And we have a parabolic curve. Let's go back to the question. The t-shirt will reach its maximum height of 86 feet after 2¼ seconds. Excellent. The range describes the height of the t-shirt during its flight. So this gets back to the issue of the difference between domain and range. Domain, recall, are all of the possible x values of the function. Range are all of the possible y values. So when you're asked what the range of this particular function represents, well, that represents all of the possible heights. Recall the t-shirt is caught at, well, 35 feet of height, so I can really consider that to be the end of our function. There we go. But the range of this function represents all the possible heights of the t-shirt in its flight. The height of the t-shirt at any time is between 5 feet and 86 feet inclusive. So the range can be stated as 5 is less than h, 5 is less than or equal to h, assuming that the shirt begins at exactly 5 feet off the ground, and h is less than or equal to 86. We can also use a graphing utility, a graphing calculator, or a site like Desmos to graph this same function. Equals negative 16 t, I'm just going to use x squared plus 72x plus 5, if I recall. Well, looks good so far. Let's zoom out just a bit on Desmos. Drag our graph to where we like it. That's perfect, at least to start. You can notice our graph begins or has a y-intercept of 0, 5. That's the height of the t-shirt as it starts. A vertex at 2.25 and 86. So after 2.25 seconds, reaches a height of 86 feet. And then this graph, this model doesn't represent the shirt being caught. We just have to realize that it begins its flight here. It peaks at the vertex of the parabola here, and it begins to fly back downward in its arc until we get to a height of 35 feet. We can find all the same information using Desmos. This is more of what a graphing calculator display would look like. If you're familiar with a graphing calculator, you can use that as well. And here's a chance to show that you have got it. In problem 2, suppose a t-shirt is launched with an initial upward velocity of 64 feet per second and is caught 35 feet above the court. How long will it take the t-shirt to reach its maximum height? How far above court level will it be? What is the range of the function that models the height of the t-shirt over time? Work carefully. And your lesson check for section 9.2.